Hi, and welcome back. Today we're going to look at the different ways that we modify metals to make them better fit for purpose for the different uses that we have for them around society. When we talk about modifying metals, generally it's because very few metals are used in their pure form. If you think about the metals that we use around the home, we generally have different things like alloys, coated metals, treated metals. It's very rarely the pure form of a metal. If you have a think, can you think of a couple of metals that you might know are being used in their pure form when we use them? One you might come across is aluminium and aluminium foil, or copper in the wires around the home. I wonder if you can think of a couple of others that are less obvious maybe. Most metals, when we use them in society, are actually used as alloys. They're mixtures of 1, 2, or even 3 metals mixed together so that we can select for particular properties. As we said, different metals vary in the way that their hardness or melting points and boiling points are affected. So these kinds of alloys, these mixtures of metals, allow us to select the properties that we're most interested in. And we can see that in things like the use of airplane parts where we want them to be light and strong, or coins where we alloy them because we want them to retain their shape, be hard, not bend too much, and be resistant to corrosion because they're handled all the time. The other way that we can modify metals is by heat treatments and by the application of coatings, so using plastics and paints and various things like that. And we will look at all of these in detail. So the first one I'm going to look at is alloying. Alloys are formed by mixing a metal with another metal. So they are literally a metallic bond that's being formed by two different metals or more. Sometimes non-metallic atoms such as carbon and silicon can be used to form an alloy, and we'll look at those. And then the way we prepare alloys is to actually melt the metals together. So you can imagine there's a lot of energy involved in this because we have to get the metal into a liquid form and melt those metals together. Okay, once we do that, we sort of make a mixture of the two metals, allow it to re-solidify, and it will reform a type of the lattice that it had before. Compared to their component metals, i.e. the ones that we mix together, metal alloys are generally harder, less malleable, and poorer conductors of heat than their component metals. This is generally because of disruptions that we put into the metallic lattice. If you remember the metallic bonding model, we said we had this beautiful array of metal cations surrounded by a delocalized electron cloud. They could easily move across each other and the bonding be stabilized. In a normal metal, if we apply force, it will shift easily, the electrons move, everything stays aligned and in order. When we add a different substance into the metal lattice, sometimes those metals will be larger, they're a little bit different, they might be atoms that are smaller. And this means that the lattice can't adjust as easily. The adjustments in the lattice tend to be a bit more over the place. We add faults into that lattice, so we tend to find it doesn't respond as well as the component metals, which is why it becomes harder, generally less malleable, it won't reform as easily. So there are two types of alloys that we need to talk about. One is substitutional. Okay, so this is like anytime we substitute something, we're swapping something out for something that is very similar. So this would be when we're using metal atoms with other metal atoms that have a similar size. Okay, so they have less disruptions to the lattice, but we can see there is variation in the size and the atoms that we use within the substitutional alloy. The other one is interstitial, and inter means within, and in interstitial alloys, the alloying component is actually fitting in the gaps between the original lattice. For substitutional alloys, atoms of the metals being used form an alloy about the same size. The added metal ions will just take up one of the positions within the organized lattice. The change in properties is a result of the new ions not fitting properly into the array, so the less malleability, the harder, usually a lower electrical conductivity. Substitutional alloys that we see in society include things like sterling silver and brass. The alloy is generally harder and more resistant to corrosion than the metal on its own. If we have a look at these alloys, so if we're making sterling silver, we will take silver, about 92.5% of it will be silver, and then about 7.5% is actually copper. So then we form sterling silver. This copper actually increases the lustrousness of the silver, making the silver shinier and a bit harder, and this is what we see with sterling silver. Brass composition, we use copper and zinc, 15 to 40% zinc, 60 to 85% copper. This makes it harder and really good for use for things like keys and pipes that we're getting a lot of use and wear on, and will hold an edge a little bit better. Common alloys of steel are made by substitutional alloying, include manganese, chromium, nickel, and cobalt. Adding manganese increases the strength and the toughness of the iron. Chromium increases the hardness and the tensile strength, and also adds a resistance to corrosion, which is why we used to have things like chrome bumpers and things. Nickel increases the toughness and the tensile strength. It also increases the hardness and its resistance to corrosion, so we will add nickel into stainless steel. Cobalt improves the magnetic properties, so if we are making creative magnets, we can use it in magnets, and we use it also in engines. You should make a note of the general things that each of these metals do, because you may be asked questions about if you made an alloy with manganese, would you expect it to be stronger, or that kind of thing, and which ones prevent corrosion. So after we've looked at substitutional alloys, remembering substitutional is when we swap one atom for another, the next one that we look at is interstitial. And we can see in this diagram here, we call the main metal cation the solvent metal, and then the smaller element is a solute atom. And this is much like what we make when we make solutions, but this time we're mixing metals and something else. So the solute is dissolved throughout the liquid metal and then allowed to solidify. Carbon steel that we use for producing a number of different things that we need to have high strength for is an example of an interstitial alloy. Interstitial alloys, the sizes are radically different, so that carbon sits between the gaps in the alloy. So steel typically is an alloy formed from carbon and iron, and then we can add other things in before. As we said, with stainless steel, you would have two alloys working at once. One would be interstitial through the addition of carbon, and then the addition of nickel would add more corrosion resistance to it as well. So low steel carbon, where we have a low percentage of carbon, allows us to increase the strength a bit, but it's still easily shaped. Bridges, buildings, ships, and things like that. Medium carbon steel, it increases its hardness. We tend to use this for large parts on large machines. High carbon steel is more brittle. Okay, so as we increase the hardness of something, its brittleness also increases. And then very high carbon steel we use for cutting tools to keep an edge on knives and things like that. The higher the percentage of carbon, the greater the hardness we have, the less the malleability we have in the steel, because all the gaps are filled between it. Things don't have much space to move and they lock in place. That increased hardness, though, does increase the brittleness of the substance. So we can alloy by adding different things in, but we can get some of the same properties in terms of hardness by doing other treatments to the metals. Because the metallic bonding model changes depending on the size of the crystals that we have, and you'll remember in our experiment we did it in agar to increase the size of the crystals, slow the growth of the crystals. The crystal structure of the metal can be altered by different heat treatments. Work hardening is a rearrangement of the crystal grains. Heat treatments allow us to control the alteration of the size of the crystal grains. And when we talk about the crystal grains, we're talking about the way that the crystals pack within the solid substance. With work hardening, what you're getting is where things bend and flex continuously around a selected point in the metal. It can happen with hammering, bending and flexing. So what this does is it causes the crystal grains to rearrange, and there will be disruption between the layers of the crystals. Okay, if you have along here, we start to see faults in the perfect crystalline structure. The crystal grains in the metal are altered. We get smaller grains being formed, and the lattice can't rearrange as easily across these faults, so it gets brittle and may crack. We get stress fractures. This is particularly important in things like aeroplanes, because the bending and flexing of the wings and the different parts while they fly can cause stress fractures. It's why it's so important that every plane after a long flight gets a maintenance check and things like that, because they look for stress fractures due to work hardening in the metal in the body of the plane. Heat treatments allow us to manipulate that crystal size more precisely. The properties of metals can be altered by controlling the heating and cooling rates to control the size of the crystals that we get. Annealing means to heat the metal to a moderate temperature and let it cool very slowly. This allows large crystals to form, producing a softer and more ductile metal. Quenching, on the other hand, means to heat the metal to the moderate temperature, sort of red hot, and then cool it quickly. You can cool it quickly by placing it into water or oil, or just letting it cool a lot quicker. This will form very small and tiny crystals. It will be a harder piece of metal, but it will be more brittle, so it can shatter. So controlling exactly how quickly you can get something in between, which gives you some hardness and a bit of brittleness, some hardness into your metal and makes it so it won't shatter. Tempering is manipulating these two techniques, where we take a quenched metal, we warm it up again at a lower temperature than initially, and then let it cool again. This reduces the brittleness, so we get a nice amount of hardness from those tiny crystals, but then we allow some of them to meld together and we get more of the hardness with less brittleness when we temper it. And you may have heard tempering in chocolate work, where you get tempered chocolate which has a good snap and shine to it, and that is doing exactly the same things, because chocolate actually has crystalline structures in it. So when you temper chocolate, you're rearranging the crystals within the chocolate to get hardness and less brittleness. So these are our heat treatment methods. Make sure that you note them. You want to be able to talk about the approximate temperatures that they're heated up to, so the heating and then the cooling. Is it cooled quickly? Is it cooled slowly? What relative size are the crystals that we get from it? And what does that do to the property of the metals? The last thing that we're going to talk about is coatings. And generally, because metals are reactive with the atmosphere and the outside world, one of the ways that we can protect them is to put a coating over the surface. This protects the metal surface from interacting with water and oxygen in the atmosphere or its surroundings that may cause it to corrode or react. Sometimes it can be done just to make something look nice. Other times it's for a functional reading as well. These coatings can be made of polymers, so plastics, which we use to insulate wires, Teflon, which we put on pots and things like that to make them non-stick. They can sometimes be coated in other metals, so galvanizing is coating iron in zinc, which helps to ensure the iron doesn't corrode, because the zinc will corrode preferentially to the iron. Also, we coat the inside of tin cans over the steel so that the contents doesn't corrode the steel surface as easily, because often the contents of things, if you think about fruit and stuff, have acids in them which would corrode the inside of the tin. That's it for our metal treatments and the last of what we will be looking at with metals. Next, we'll be moving on to ionic bonding. So make sure that you have your notes all settled, you're confident asking questions, and be sure to check anything that you're unsure about with me in class.